My name is Tim Kraska. It's a real pleasure to be here. I'm going to talk about how will AI impact database systems. Before I go really into the weeds, let me give you a short disclaimer. So I have a double role. On one hand, I'm a professor at MIT, but I'm also now a director of applied science at AWS, where I lead the Learn Systems group, working particularly on how to apply machine learning to systems. However, in this talk, I will talk in my role as an MIT professor, and in no ways are the following slides representing the views of AWS. I rather want to focus on some recent results from the research community and give you an idea about where the field is heading. So for the agenda for this talk, I want to cover two things. On one hand, talk about the evolution of automatic systems optimizations. I will spend most of my time on that topic, but given the recent hype around generative AI, it's hard to ignore it. And I will also cover a little bit at the end how we believe generative AI, at least from an academic standpoint, will change the field of system, particularly database systems. So starting with the first one on automatic system optimization. So why are we doing that? On one hand, like Moore's law is coming to an end. And I think this should come to no surprise to many people here. What that means is Moore's law defined for a long time the advancements in computing. So essentially it says like that every 4 years, the processing power doubled. However, that is coming to an end now and it's slowing down. And there are a bunch of like studies done around that. It's mainly we are hitting the limitations of physics. So people are working around the globe on what to do with that and how to address the slowdown. At the same time, though, data is increasing in an unprecedented speed. So what that means now is like the computational power is not increasing as fast anymore. It's actually slowing down, where still the data amount is increasing. So in order to deal with like this increased amount of data we nowadays have, we need to come up with new solutions. And one way to do that is actually called specialization. And we already see that happening on the hardware front. For example, GPUs, TPUs, and FPGAs are all forms of specialized hardware, which then are able to get more processing power because they are just focused on a specific functions, let's say array computation. What the research community is currently wondering around is, can we not apply a similar concept to systems? Right? So can we specialize systems, let's say, to the workload and the data to get better performance out of them, to deal with this onslaught of data we will face now and even more in the future? So this idea on its own is actually not even new. All systems nowadays have a whole range of knobs which can be tuned. And traditionally, a database administrator would be doing that. However, more recently, machine learning has been applied to automatically tune these systems based on the workload and the data. So like every system you know has a bunch of knobs, let's say the buffer size, or it allows you to create indexes and materialized views. And now techniques are developed to make that more automatic. And those go actually back to the 90s. So they have been around for quite some time. Yet now we see them actually appearing in industry and they are really productionized. However, we are trying to look beyond that. And what like currently a very hot topic in the research community is what we call learned components. So these are components which go beyond traditional knob tuning. They are like new concepts where normally machine learning is deeply embedded into a component of a system to provide even better performance, often way beyond what traditional database administrators or other types of system administrators would be even able to do because they have so many parameters. They are not like human understandable anymore. Eventually, what we want to get to is what we call an entire instance optimized system. So a system that self-adjusts to the data and the workload in ways otherwise not possible. So for the rest of the talk, I would like to give you at least some idea about some of the recent learned components which have been developed in the research community, and then also show you some results, like very early results on an instance optimized system. So over the last years, like my research group and many others have been working on these like so-called learned components. On this slide, you see like a few of the components we have been working on, from indexes, materialized views, Bloom filters, range filters, sorting, and so on. In this talk, at least I want to give you a high-level idea what a learned component is, starting particularly with indexes, and then afterwards we will talk about multidimensional indexes and query optimization. So let's dive into our learned components, particularly for indexes, which is like one of the standard structures to find data in a database system. For example, Aurora, RDS, like most of the engines they use, they support indexes in one way or the other form. So what is an index? So imagine you have a library and you're trying to find a book in the library, let's say the Harry Potter book. One way to find a book in the library is by consulting a catalog, right? You have this like index cards which tell you the location of the book. If you have a very large library, probably you don't have just like one of these boxes with these index cards. You have like several drawers and potentially an entire room of like every single book, and every book has an index card in these drawers, and you need to find one. In order to do that, normally these drawers are all alphabetically organized, let's say by author. So now if I'm looking for a book or like author or title, now if I'm looking for a book, like let's say for Harry Potter, what I would do first is like I'm looking for the right cabinet, and then I drill further down. This turns out to be the same structure which normal databases use to find a particular single record in a large collection of data, right? And that's called a B tree. So how does it work is you start out with the cabinet, which is the top root node of a B tree. Based on that, you drill further down now to the drawer, which is like in the case of a B tree, again, you're traversing the B tree to the next node, which then eventually gets you the index card. In the case of a B tree, it would be the position where the data is stored, for example, on disk or in my memory. Right? So in the end, finding some data item is nothing else than looking for an index card in this like large like organization of like drawers and cabinets, organized or sorted by title or author. However, there's an alternative way to find something. So if you enter the library, probably your first step wouldn't be to go to look for the right index card. Rather, you would ask a librarian to tell you where are the Harry Potter books. And the librarian has a rough mental model where the books are stored inside the library. For example, he would probably point you to like, oh yeah, Harry Potter, children's book, please go up to the children's section, and then look at the bottom like side at the right corner. Even though the librarian doesn't entirely know the exact position of the book, he can point you in the right direction, and then you do some local search around this area until you find the book you're looking for. Even better, like the librarian, what he has is essentially mental model. Even better is now, like if he figures out that certain books are more often like searched for than others or more requested, he's able to reorganize the library in a way so that his mental model fits the access pattern, right? So for example, if he figures out that like children's books are often requested, particularly Harry Potter, maybe he puts them in the bottom so that it's more easily findable. So in the end, what that means is that we took the index card in these like large drawers and we just replaced it with the librarian. So one thing we were wondering as part of my group is, can we not do something very, very similar with B trees, which is the standard structure to look up data on disk, and replace that with a model which roughly tells you where the data is stored, and then go from there. It turns out that this is actually possible. If we assume the data is sorted, what we can do is we can build a model over this sorted data, which turns out to be the cumulative distribution function, which is nothing else than a special form of a probability function. And if we then ask for a particular item, let's say Harry Potter or a date in this case, it points us roughly in the right direction where we would find this record in the sorted set. Now, this model might be wrong. However, given that everything is sorted at the bottom, we can apply some localized search to find actually the record we are looking for. So in the end, by cleverly combining models with some more traditional search techniques, we are able to develop a data structure like the traditional B-tree, which gives you the exact same guarantees. So it's not an approximate structure. So if the record exists, it's guaranteed it will find it. So we don't change any semantic. But potentially, it might be a better structure, like this librarian, because it could potentially faster find the record you're looking for. So why does it actually matter? We did large studies around that. And for example, we found that this approach, which we named learned indexes, can be up to 10 times smaller than their traditional counterparts and up to 2 times faster in lookup performance. So we published this result, like the original one, in 2018. We did a lot of follow-up work and benchmarking studies with that. But interesting enough, this whole topic around learned indexes, so how you can leverage machine learning models to replace actually traditional data structures, became a whole research area on its own. And there has been a lot of follow-up work. For example, we see that this same idea was applied in bioinformatics and other systems work and theory values and so on. So this became a very, very active research area. So moving on to multidimensional indexes, and that's something we are very, very excited around right now. So what is a multidimensional index? It's very related to what I showed you just before. It's again an index structure, but it tries to do something for requests which filter by several dimensions. So let's assume you have a query here where you try to find records, for example, of customers, where a customer is in a certain age and salary range. The problem now with this request is that in order to normally speed it up, let's say in a data warehouse, the standard technique is to sort the data either by age or by salary. Right? So assume the picture here on the left. What you have here is all the data points which are somewhere in the range of salary and age. What we are looking for are the ones in the green rectangle. So now if we would sort, for example, the data by age, which is sometimes also called a sort key, we would still need to scan all the red regions, all the records which don't fall into our salary range. Whereas if you would sort by salary, we have the same problem with age. Right? So this is what we call the scan overhead. We are scanning more items than we actually need in the end if we pick a sort key, which is over let's say 2 dimensions. So ideally what we want to do is just reduce the numbers of records we need to scan in order to return a result. And our technique is just by imposing a grid, a multidimensional structure over the data. So now if you see this grid, the question becomes a different one. It's how do you structure the grid? And the answer here is that we can make it workload dependent. Right? So depending on the workload, we figure out if the grid cells should be longer, smaller, taller, and so on. And this highly depends on the queries of the workload as well as how the data distribution looks like. So we did this as a part of work which was called FLOOD. The citation here is at the bottom. We later extended that as part of a new project called Tsunami. The biggest difference between FLOOD and Tsunami is that FLOOD allows you to organize different parts of the data in different ways. And this, for example, reflects the fact that often, let's say, dashboards do different types of queries over the last months than over the last year. The results from FLOOD and Tsunami are, again, very, very promising. So here we tested this technique on 2 data sets, which you can find in open source, Taxi and Performance. They're mentioned in our benchmark, regarding the average query time and regarding the index size we created for finding the data. So where you want to be is the left bottom corner. And we compared Tsunami in blue against FLOOD, our previous technique, in orange, and then against other typical multidimensional data structures like clustered indexes, KD trees, Z-order encoding, or hyperarc trees. These are more the traditional counterparts. What you see here is that for FLOOD and Tsunami, we are often able to outperform the traditional counterparts by an order of magnitude in size at lookup times. And that can be a really big deal for many workloads, right? You should also notice here, if you look at the graph, that actually both the X and the Y axis are in log scale. Okay, now let me give you, before I move on to the other talk, with a very brief overview of like another area we are very excited about, and that's query optimization. So what does query optimization do? So any database you use, you start with a SQL query. Normally the SQL query then goes through a parser, then it goes to an optimizer, which consists of a bunch of rules and a cost model. Based on the optimizer, it creates an execution plan for your query. The execution plan then gets executed, and you get finally your result back. This is a traditional query optimizer. However, if the query optimizer does a mistake, traditionally there is no feedback loop. It doesn't get smarter over time. So we started a project which we called NEO, for Neural Optimizer. And the core idea is that instead of having this like traditional handcrafted cost model and a bunch of transformation rules, that we actually learn large pieces of it and replace it with a neural net. So now we introduce this feedback loop. And now if, for example, the query optimizer picks a plan which is not optimal, it re-optimizes it and finds hopefully over time a better plan. The problem with this approach is that often the training time can take a long time, and it can lead to very hard to understand decisions. So more recently, we actually tried to improve upon that, and we developed BAO, which is a way to improve a traditional query optimizer, let's say the one from Postgres or other open source systems. It works by using the traditional optimizers and then creating variants from it through what we call hint sets. So essentially, a hint might be, please don't use nested loop joins, because they can be very bad if you pick the wrong join order. And then we developed a whole bunch of like machinery around it, again, based on neural nets and other techniques, to learn which hint sets work best for which types of queries. So looking at some performance numbers, so this is just like an experiment we did with Postgres. So this is the traditional Postgres execution time. You see on the y-axis how many queries finished over time in hours on the x-axis. If you would use NEO, in the beginning you see a slowdown because the optimizer needs to learn first what works and what doesn't work for the particular data and workload, but then eventually it goes much faster. With BAO, on the other hand, we see like a speed up almost from the get-go because it learns way faster than the NEO approach, and actually gets pretty good at it. Even though at the very end you see NEO becoming better because it's simply able to learn more. Okay, so what we have seen so far is just like on how indexes as well as query optimizations can be enhanced using AI techniques. What I'm showing here on this slide is the standard database architecture by Joe Hellerstein's book, which splits up a database into different components like query optimization, access methods, and other things. So what we focused on in this talk was mainly access methods and query optimization. However, people looked into other components as well. For example, people have looked into scheduling, as I mentioned, query optimization. People looked into admission control, buffer management, log manager. So each of these components here in pink, I can actually at least mention one research paper which tried to make it more like learning enhanced or instance optimized. Right? So we are clearly fundamentally changing the whole database system through AI components and machine learning techniques. However, up to this date, what hasn't been done yet is what we call the last stage, to develop a full instance optimized system and figure out a way on how these different components actually work together. At MIT, we started a research project around this, which we called SageDB, which was our first attempt to build a full end-to-end optimized system, which is instance optimized. So it entirely learns based on the data and the workload. And we tried to figure out how far we can push it. So we developed this prototype over the last year with some very interesting results. So here, what I'm showing is like one of the evaluations we did on one workload, Bitcoin. If you're interested in more, I mention again the paper citation at the top. But what you see here in this first slide is we took Postgres, we ran it over the Bitcoin workload just out of the box without any tuning. On the left side, you see the latency it took. On the right side, the size of the database. Right? So after tuning, the latency got better, the size increased, mainly because the expert tuned version created indexes, materialized views, and other things which take space. We also compared it against a commercial system. And in this case, you see the commercial system actually has much better performance, even out of the box. But with expert tuning, you could manual expert tuning, you can increase the cost even further at a very high cost of storage capacity, because essentially what the expert did in this case is tuned the system in a way by creating a lot of materialized views, so pre-computing a lot of the results. Now, looking at SageDB, it's achieved even better performance. So we almost got a 10x out of it at a moderate cost. And I think that's pretty remarkable. This result, I have to say, doesn't include many of the optimizations I mentioned here. For example, it didn't include the multi-dimensional indexes or the query optimization. It includes techniques like partial materialized views and some of the other ones we have been working on over the last couple of years. So there's still a lot of optimization left. So I'm almost at the end, but any AI talk on how AI changed system wouldn't be complete if we at least not mention generative AI. And the academic research community certainly currently is looking heavily into what LLMs, large language models and foundational models, mean for systems. There are some obvious use cases like English to SQL. It has a very long history. People looked into it in the 90s already. However, the foundational models now, I believe, make it for the first time a really viable option, because it became so good that it actually can be used in production systems. But there are also many other interesting areas which might be a little bit more surprising. For example, I talked about knob tuning. There has been recently a paper by Emanuel Trümmer called dbbird, which tried to leverage large language models to automatically read the manuals of database system and then use that to tune the system afterwards. I thought that was a very interesting approach. Clearly, large language models will have an impact on data integration, schema matching, many related things, entity resolution. There are, I only mentioned one paper here, which applied deep entity mentoring, so large language models for entity resolution, but there are many more papers now coming. I'm aware of a large amount actually over the last few months. So these are kind of obvious use cases. I think what I'm very excited about are the ones which are even more forward-looking. Again, Emanuel Trümmer had this very interesting paper called CodexDB, where he tried to figure out a way on how we can leverage large language models to build entire systems. It's very early stage, it's very far out, but it's still an interesting approach. At MIT currently, we are looking into how we can leverage large language models for automatic data mesh creation. So essentially what we are after is creating one unified interface, which under the hood then uses specialized engines like a data warehouse, a transactional system, a document system, and so on, but gives the appearance of one single system and everything gets automatically handled underneath. There are many other things currently going on around foundational models, which unfortunately don't have time to cover. However, I'm more than happy to chat to people over email after this talk, so please shoot me a message. And with that, thank you again for listening. And again, it was great to be here. Thanks.